All right, we might get started as a couple more people dribble in. So today we welcome Frankie Cho, who will be familiar to most, if not all of you. Frankie is currently a research fellow at the Centre for Biodiversity and Conservation Science, that's us. His current work investigates the impact of land use policy on koala habitats in New South Wales. He has a background in geography and is expected to complete his joint PhD in environmental economics at the University of Exeter and the University of Queensland through QX joint doctoral program. But you did complete your PhD, yeah? Or you just...
Yeah, I'm waiting for the Bible.
Okay, yep. In his PhD, he focused on applying cutting-edge decision science techniques to reduce the effects of climate and economic uncertainty on policies that aim to improve natural capital resources. He has a long-standing interest in the synthesis of novel data and decision science techniques to guide policymakers to solve pressing environmental problems and improve the effectiveness of conservation activities. With that, Frankie, over to you.
Thank you. Thank you, Simon. So, welcome to the talk today. I'm pleased to share with you some of my work that has been going on during my PhD to try to improve the planning tools that we have in conservation and decision science to incorporate risk and uncertainty about our future into planning. But first, I'd like to acknowledge the traditional owners and custodians of the land which we meet today. Today, we are meeting at UQ, so that's Toowoomba and Yagara land. And these are lands that has been owned by the traditional owners of Australia. And also they recognize their global contributions to society, and we recognize that they have rights to the land that's never been seen before. And it's particularly important to think about Indigenous populations when we are thinking about global environmental challenges, because whilst they are likely to be really strongly affected by climate change and the uncertainties that we have in the future, they are also likely to be able to provide the wisdom and the knowledge to manage landscapes in a way such that we make our way through some of the global environmental challenges that will come today. So I just want to acknowledge the importance of the traditional owners to the work that I've been doing, but I'm also, of course, also guilty of not being able to think more carefully about some of their approaches, and I encourage the CBCS community to think more about Indigenous concerns and incorporate their knowledge in decision making and planning for conservation. So we know that there's a couple of things that we already know about the literature. So firstly, we know that global land use planning and spatial planning is needed in order to meet some of our global environmental commitments that Australia and most industrialized nations have signed on to. So firstly, we've got the Paris Agreement that we know that limits temperature increases to 1.5 degrees Celsius. The question is, how can we get to that? One of the approaches is being Trillion Trees initiatives or the United Nations Decade for Ecosystem Restoration, where they're thinking about restoring ecosystems on a large scale that requires setting land aside from production, from agricultural production, from urban development, and so on and so forth. So it requires really careful and at the same time large-scale planning and alterations to the status quo for how land is being managed at a grand scale. There's also the Global Biodiversity Commitment, which a lot of you are familiar with, which is broadly known as the headline commitment. It's multiple different targets that are covered in the Global Biodiversity Commitment, but the headline target is the quote-unquote 30 by 30 goal, which is to protect 30% of ecosystems by the year 2030. So that also implies us setting aside land for protection, protected areas, and trying to protect our vital biodiversity and species. So that's what we know. We know that these commitments cannot be met without proper land use planning. And that point is emphasized in the Global Biodiversity Framework, Target 1. So they started off their targets by making a point and emphasizing that there is a need for participatory, integrated, and biodiversity inclusive spatial planning. So it means that we need to plan our protected areas in a way such that it includes the multiple aspects and considerations that we have for planning protected areas. So how can we actually achieve this? So one way that a lot of people at CBCS are advocating for and advancing and adopted widely across the world is an approach known as systematic conservation planning or spatial planning. These are approaches where we think about the problem in a more systematic way. We would a typical way of conducting these exercises for conservation planning would be to collect data around the costs and the biodiversity benefits of protecting species across space. And the idea is that, well, after we collect these layers, which a lot of people at CBCS are working towards collecting, particularly biodiversity data, collecting data about the species distribution models, for example, we then formulate explicit objectives. Say, for example, in this case, we wanted to achieve a biodiversity target at the minimum cost. Or in the reverse, we have a budget we want to spend, and we wanted to maximize the amount of biodiversity we protect. So we've got an objective, we're very explicit about the objectives, and explicit about the constraints, and in the end, we end up with a spatial plan. So that's areas where we want to choose for conservation, for protection, or for ecosystem restoration. And in the end, we get something like this. We see the total expected total costs of our conservation plan, as well as the projected biodiversity benefits in a bar chart. Well, then that is nicely done, and we've got our spatial plan as the best in terms of biodiversity and also balancing other needs. There's and we try to optimize it, and we use a lot of approaches in mathematics to do this. Previously, we tried to use what's called simulated annealing approaches to identify the spatial plan across space. And recently, we are using techniques known as integer linear programming to achieve the similar objectives of optimizing for biodiversity whilst minimizing costs. There's a challenge, however. There are many challenges that affect this approach. One of the most recognizable one is climate change. So just to give you some indication for the projected magnitude of how climate change could affect our conservation plans. So we've got research by Conradi and others in Nature Ecology and Evolution that shows that if we account for these climate change uncertainties, 68% of the terrestrial surfaces on the land, we think about protection on land at the moment, will experience a substantial change in the phytoclimate, which is the climates that are suitable for plant growth at year 2070, which means that there will be a drastic change in the plant species that are growing in the areas that we want to protect after we protected, assuming a high emission scenario, assuming that climate change goes relatively unmitigated. There's other evidence that shows that 87% of the ecoregions, so what these researchers, Dabrowski and others in Communications of an Environment shows is that if we split the world up into different ecoregions, and they try to find that whether or not we can find enough climatically stable and intact land for conservation to meet our 30 by 30 goals. And they found that, well, actually, in 87% of the ecoregions they are not able to find enough land that are climatically stable and also intact, which means that if we account for climate change and its impacts on biodiversity, it's much harder for us to reach the 30 by 30 goals and achieve robust protection of our valuable biodiversity. But there's more to that. Biodiversity is only one aspect to thinking about the conservation planning problem. We also know that socioeconomic uncertainties are something that we need to think more explicitly about. And these affect the costs that we have for conservation and the benefit and the overall cost benefit calculations that we end up with in a conservation planning exercise. So, for example, these researchers, Bailey Weiss and others in environmental research letters, shows that there will be a projected 80% increase in the food prices associated with large-scale afforestation across the globe. That means that if the food prices are increasing, the opportunity costs of agriculture arising from protecting land will increase, and therefore it will affect the costs that we have for protection across the world, for protecting and restoring our ecosystems, because we are fundamentally setting aside land from agriculture for protection and restoration. There's also other studies that shows that the alternative of like thinking about ecosystem restoration, thinking about aspects such as tree planting, for example, these generate economic costs, and these researchers here, Payne Winkle and others in Nature Climate Change, they show that 34%, there will be an expected drop of the value of forests in general in Europe by 34% under a climate change scenario. So that means that if we try to bring in economics, there are a lot more other uncertainties that we have to think about more explicitly in a conservation planning problem. Then how does that affect our problem here? So we see that we typically think of a conservation planning problem as a bar chart right here. We've got the costs and we've got the benefits. But in reality, it looks more something like this. It looks like a distribution of possible outcomes. Outcomes that we cannot know for certain at the present time step when we make decisions. This is a problem because, as we can see here in the biodiversity distribution, there could be a chance that we are actually meeting our actual targets for biodiversity under a very small subset of our realized future. So we are not meeting our biodiversity commitments robustly, is what we're trying to do here, what we're trying to say here. We could meet it in some state of the world, but there is a large chance that we don't meet it because of uncertainty. So when there are uncertainty, like how can we still approach this problem, right? When there are uncertainties coming from all different angles, from climate change, from socioeconomic variables that affect both the cost layer we have here and the biodiversity layers over here, how can we approach that problem? There are a couple of ways that we can try to address this problem. So let's say on the left-hand side, we've got the protection restoration, that these are the areas that we identify in a conservation planning exercise that are suitable for conservation. And these are the objectives on the right-hand side where we are faced with a distribution of possible outcomes. Well, one way we can do it is through robust planning, which essentially means that, well, let's protect more, right? Let's protect more areas and we can boost our biodiversity at the expense of higher costs. Of course, the problem is that we are incurring a much higher cost for achieving these targets. It's much less politically palatable to our decision makers, but at the same time, we achieve our biodiversity commitments at a much higher probability. However, there are other ways that the literature is suggesting that we approach this problem. So that's what's called a risk-sensitive planning. So that is, for example, if we, let's say, diversify across the planning extent by selecting planning units that are far away from another, there's a much lower chance that one risk factor is going to affect all our planning units at once, and therefore we are reducing the amount of variability in the outcomes that we get here. So this is a hypothetical example where we can potentially reduce the variance on the right-hand side of the outcomes by diversification, by diversifying across different locations. But there are many other different ways we can achieve that, aside from just selecting better location. In my PhD thesis, I summarized a couple of ways we can achieve that. So firstly, is through choice of location. So by selecting combinations of planning units with lower correlations in its outcomes, then we are able to ensure that if one planning unit does well, or one planning unit doesn't do well, there's another planning unit that does relatively okay. That means that we ensure robustly that our planning targets are met. There's also species choice here. So for example, if we choose different species, maybe we can achieve a better outcome because maybe one species for tree planting is affected, another tree species remains okay. So that's the same logic that follows from the typical finance literature of diversification. There's also the third approach that I'm going to cover, which is a flexible adaptation approach, where we intentionally delay some of our decision making for planning units that we are uncertain about into the future. And I'll show you what sort of effect it would have to your planning problem. And when we extend this problem to not just selecting planning units in one time step, but multiple different time steps. So let's focus on the first two approaches in the first case study, which is a risk-sensitive tree planting example I have in the United Kingdom. So the UK, just like any other major industrialized nation, has signed on to treaties that require it to reach net zero by 2050. And one of the components of that strategy is through massive tree planting. So they are proposing to plant 30,000 hectares of trees every year across the UK by 2025. And that will be expected to sequester 12 million tons of carbon or equivalent every year. And also, and it would approximately take 21% of agricultural land out of production. So that policy will have major ramifications to the agricultural production in the UK. So what we then did was to construct what's called illustrative scenarios. So there are many different possible outcomes in the future in terms of the extent of climate change and socioeconomic variables. It can be best represented through a distribution of possible outcomes. But to select a couple, we selected a couple of scenarios, and it's important to recognize that these scenarios that we selected are not just RTPs, not just representative concentration power, because it represents a co-evolution of climate and also other socioeconomic variables. So say, for example, in the near historic scenario over here, we assume a RCP is consistent with a RCP 2.6, so that's radiated forcing that is 2.6 above industrial pre-industrial levels, and we can then project a whole host of changes in the other key variables that are driving tree planting exercises in the UK. So, for example, we projected changes in wheat, in beef, and in many other agricultural commodities that affect the opportunity cost layer that we have. And then these are some of the results. As you can see, there's a huge variability that we try to represent here in a case study, but we encourage decision makers to think more explicitly about uncertainties and the sensitivities of their decisions with respect to changes in future socioeconomic variables and also climate variables into the future. So we fit these scenarios through what's called an integrated environment economy model, which is an approach that allows us to relate the changes in key variables such as climate, such as agricultural market changes, timber value, and what's called the so-called social cost of carbon, which is the value society places to sequestering carbon. And then we relate these through a series of statistical models that have been fitted on historical pattern to understand what the natural capital value of these tree planting would be. So for those who are not familiar, natural capital refers to the stock of renewable and non-renewable natural resources. And by planting trees, we are generating new natural capital that can be quantified in many different ways. So one of which is being the cost. If we consider the cost of foregone agricultural profits, and we also consider benefits from not just income from timber harvesting, but also the value of carbon through sequestration, and also its relative changes in biodiversity. These are things that we think explicitly about when we adopt the natural capital framework. So as my analysis shows that if we adopted different assumptions for the future, we can actually radically change what's known as the optimal solution that we find in a systematic conservation planning problem. On the left-hand side, we see the near historic scenario, and we plan under that scenario. We are planting almost all coniferous trees in the UK, and on the reverse, if we are assuming a high emission scenario, we'll be planting most, if not all, broadleaf trees. So we identified that these conservation or systematic planning approaches are actually highly sensitive to what we assume about the future. And moreover, it's not just that would change the decisions that we would be making, or what we would think of as optimal decisions. It will also change the natural capital value of tree planting exercises. So depending on which scenario we assume, the best recommendations could in fact become the worst recommendations if we all simply alter the scenario that we have in the future. And it's important to remind you that the tree planting example and many other decisions in conservation planning and ecosystem restoration are highly irreversible. It means that if we put in trees today, then it's really hard for us to reverse these decisions into the future. And if we zoom in a little bit to look at multiple different sites and to look at how this would play out on a local scale, we can sort of explore that the net present value for, let's say, planting in this site in Scotland would be would strike at the 0 line, which means that there could be some chance that the net present value of tree planting is negative and some chance that it would be positive. And the question is, does that change if we selected another site? And I tried many different sites, and of course it did not. Most sites of tree planting in the UK, we observe a net present value that is strikes at 0. So it doesn't. We are highly uncertain whether or not tree planting will actually deliver net positive social benefits. But we are quite certain that it would change or improve the amount of species that we observe in terms of 300 priority species in the UK. So if we overlay some of the climate economy scenarios that we introduced here, a pattern emerges that if we assume a high value of carbon in the future. So let's say we assume that the value of sequestering carbon is high in the future, then the net present value is most likely positive. These tree planting exercises will generate net benefits to UK society in this case. Whereas if we assume a near historic scenario, we most likely end up in a loss. But still, it would be relatively okay because we are not as embracing that much climate change in the future. And then the next question is, does diversification help, right? So let's say we diversify and we view these two sites, planting in Scotland and planting in the east of England together. We think of these together and we try to say, let's say this is a diversified portfolio. Let's plant in many different places, view them all together and see if that actually helps improve the solutions. So we find that the net present value here on the bottom, the variability does shrink a little bit, but still there is a huge chance for us to experience some sort of net negative in terms of the social value. So it sort of shows that diversification to some degree would help, but it would not completely eliminate the problem. So as we can see, if we reduce risk, then strategically, then we are able to reduce the variability in the net present value. But at the same time, we also know that these diversified portfolios might not necessarily lead to the largest net gain in terms of the biodiversity outcomes that we see. So let's say, here we've got asset 1 and asset 2. These would increase. We would see an increase in the species, change in the species compared to the baseline, which is the triangle here. But for asset 3, we're not seeing a lot of improvements in terms of the species richness. Maybe probably because these have a relatively high baseline to begin with. But that's something that we have to explore further. But taking all of these together and trying to identify a diversified planting portfolio in the UK, for me, it did not yield a lot of success because we know that a lot of the risk factors that are present in the UK are affecting quite homogeneously most planting locations in the UK. So let's say climate change is going to affect the productivities of trees across the whole of UK. Likewise, the changes in the social cost of carbon will also introduce highly correlated uncertainties. So when these highly correlated risk factors exist, even the best risk-averse or risk-sensitive planning tools may not actually lead to a dramatic reduction in the amount of risk that we have. So in this case, we show that by moving from a maximization of expected value approach to a highly risk-averse approach, where we explicitly minimize the downside risk over here, the downside risk being the outcomes that are much worse than expected, we would reduce the chance of the UK experiencing net total losses for £10 billion or more from 9% down to 5%. And we see that by adopting some of these risk-sensitive tools, yes, we are reducing the worst outcomes for some of these scenarios, but at the same time, we're facing substantial trade-offs in the amount of upside gains that we get when society turns out to be a different scenario. So there are always important trade-offs that we need to think about when we deploy these risk-sensitive planning tools. So some of the takeaways from this study is that when we deploy spatial planning tools, we know that these planning tools are inherently highly sensitive to future climate and economic conditions. And we also know that diversification is not a magic bullet. It helps, sometimes it helps, but maybe sometimes the outcomes that we get are not as dramatic as we would have thought. There's also a high correlation of risk when there is a correlation of risk, and that echoes some of the works that have been done by, let's say, Rebecca Runting, who's at CBCS, and also a group by Amy Ando and others, that shows that if we have highly correlated risk factors, then some of these planning tools might not be highly effective. So these are some of the takeaways that we can extract from the UK case study. And it's not the best result that I wanted, but that's the result that I've been getting. And in fact, it's a relatively strong message for what the limitations of these spatial planning tools are. So as we move on to some of the other approaches that we can potentially deploy to reduce the amount of risks that we have in spatial planning, we can look at a flexible adaptation approach, and that's work that I've been working on with Jonathan and Brooke and other people who are in the room today. So that is an approach where we strategically plan for adaptation activities for koala conservation, in this case in New South Wales in Australia, for protecting the endangered koala. So the koala has obviously attracted a lot of national attention. Us being in Australia is something that a lot of people are thinking about. And I wanted to also stress that protection of koalas will likely have other co-benefits to protecting biodiversity of other co-occurring species as well. But especially for the koala, it's recently declared endangered in 2022 in Queensland, in New South Wales, and the Australian Capital Territory. So that's why it's attracted so much attention in Australia, and there's a lot of public funding that has been trying to go into managing threats to koalas and reducing its impacts, particularly on climate change. So in this case, I focused on trying to test out a couple of strategies over time to reduce the impacts of climate change, reduce the effects of climate change on our strategies to protect koalas on private land. So we've been looking so far with at inflexible strategies, right? So that is what typically we do in a conservation planning exercise. Let's say we optimize our objective and found the best solution, and we just place protected areas in the first time step. That's right now. Let's assume that we place these protected areas in there and let it play out under climate change. And we know that climate change is going to have continued effects on the effectiveness of these protected areas. So what sort of effects we might say is that, let's say if we ignore some of these risks going into the future, we would see that the amount of diversity that we protect on the y-axis would decrease. The effectiveness of these protected areas will continually decrease under climate change. So that's a problem, because there is actually a lot of chance for us to not reach our target in these cases, depending on how we set up the problem. We can, as I mentioned, adopt robust planning approaches where we just try to protect more, right? We can protect more habitats for koalas or other species, and we can ensure that even there's a decline in the overall habitat quality, and there's also variabilities that are associated with the our knowledge or understanding of climate change. We still sort of meet our targets, but as I will show later, that implies that we spend a lot more money on conservation. There are other ways we can do it, right? There are ways where we can first plan in the first time step, T1, and then we adapt, right? We adapt in the second time step. We modify in some cases where possible, modify the conservation actions that we have, or in my case, I explicitly look at just adding in new protected areas, which is something that's more politically feasible than, say, modifying or changing protected areas as we go on. So that will have some effect, right? So if we are flexible, then it means that we invest in the second time step to expand our protected areas, to reduce the effects of climate change, ensure that we continually meet our biodiversity targets, or we can use that time that we have between the time 1 and time 2 to actually learn something about the broad effects of climate change. So that would imply more investments into learning and resolving uncertainties around ecology and as well as our climate system. And we can actually reduce uncertainty. Let's say we completely eliminated uncertainty through further research during these 2 time periods, then we are actually, let's say here, we are able to still reach our targets with much less investments in the second time step. So we leverage learning opportunities to reduce our uncertainty and improve the effectiveness of spatial targets, our spatial targeting efforts for managing emerging threats and our declining biodiversity. So some of the results that we observed here is that if we are, as I pointed out, if we are inflexible and if we ignore risk, then there's a huge chance here that we experience a high amount of, there's a huge chance that we don't meet our targets, basically. It means that it could be even below as like 20 or 30%. There are chances that we only meet our target at 20 to 30% in some outcomes. So that's not something that we want to, right? We want to ensure that our conservation efforts are well spent and well directed, and we want to ensure that a policy target, when we set it at 100%, is always above 100%. We can deploy a robust approach where we ensure where we have more protection, and we ensure that the policy target is continually met, or we can deploy flexible approaches that incorporate learning about climate change, and that can also ensure that we meet our targets continually over time. And why would we want to do a flexible approach compared to, let's say, a robust approach, you may ask? It's because that it's much more cost effective. We quantified that if we adopted, instead of a robust approach, used a flexible approach that allows us to put in new protected areas in a later time step, we are, if we did not incorporate learning, even if we did not incorporate learning, we are able to achieve the same conservation goals at roughly 30 to 40% lower conservation costs. And if we incorporated learning, this decrease in the conservation costs reaches up to 50%. So that's a massive decrease in the amount of money that we need to spend to protect the same amount of species, and therefore a higher level of cost effectiveness in our conservation program. And we also know that if we allow for these flexible approaches, why do we have to think about now, right? We can, a reasonable question to ask is that if we don't need to think about these now, we can just do what's best for now, such that in the future people can do the people in the future can do what's best for them. That's not what we found to be the best way of thinking about this problem. Here we know that if we ignore risk and here we quantified what sort of properties we would invest in for conservation for koalas in the first time period and also the second time period. And we found that if we adopted a flexible approach, we would actually have much more very different investment priorities in the first time step. It means the decisions that we're making now would be different if we adopted a flexible strategy and we want to realize some of the benefits that I mentioned earlier. So particularly, we found that there's only a 30 to 45% overlap in the amount of in the properties that we want to invest in now for the strategies that are inflexible versus the ones that are flexible. It means that if we invested or used a strategy that is inflexible in the first time step, in the second time step, we are not effectively keeping options open, we are not effectively enabling adaptation opportunities. We're not opening up adaptation opportunities in the future. It makes the job of the future decision maker much harder because we are committing to a lot, we are investing in a lot of properties right now that could fail under climate change. We are exposing ourselves to much higher risk if we adopted an inflexible approach. So some of the takeaways from this study is that we know that firstly, if we adopted a robust approach, we can still meet our targets. There's no problems with that, and we can still meet our targets on the climate change, but it's going to come with a substantially higher cost. If we adopted a flexible approach, we are able to we need to identify conservation investment priorities simultaneously for now and the future, because by adopting some of these approaches, we are able to select which properties we should invest in now versus in the future. Most likely, it's the properties that we are much less uncertain about that will benefit from conservation right now, and we wait for more information and knowledge about climate change before committing to irreversible decisions for properties that we have less information about in the future. So it's important that's why keep options open, because by keeping options open, we are reducing a lot of the conservation spending towards properties or conservation protected area that will be made ineffective under climate change. So I just wanted to wrap up the discussion today by thinking more about how we use these planning tools to meet our global biodiversity commitments and climate commitments. So there's a huge potential for appropriate spatial planning, and there's an increasing emphasis on thinking about risk and uncertainty about climate change. And what we're trying to do here is to try to incorporate some of the ideas from risk and in finance, in quantitative operations research, into trying to thinking more about risk and uncertainty in some of these conservation planning problems. There are a couple of other issues, obviously, to think more carefully about when we try to bring these to the ground. One is that whether or not some of the planning approaches that I've recommended here is actually possible in some of the, depending on the governance institutional arrangements of conservation organizations across the world. As we know, the 30 by 30 goals are just up to 2030, right? So it incentivizes a shorter term thinking about conservation and thinking about policymakers are trying to rush to get to the 30% goal. And a lot of times, a lot of the adaptive longer term thinking gets missed. We can imagine a scenario where in 2030, policymakers celebrate and say, well, we've met our 2030 goals, but we are not thinking about the continued effects on climate change on the protected areas that we have. And then it would really contribute to ineffective conservation policy. There's also a added question about when we think about these global commitments and think about how to action on them on the ground. A lot of times it's actually incentivized through economic incentives rather than direct targeted payments or direct selection of different sites across the globe to perform these environmental actions. So the question then becomes, how do we actually not think just about selecting properties or selecting areas on the map to conserve, but thinking about how we design economic incentives around some of these activities. So I have a paper recently published around the effects of, if we thought of instead of not just about site selection, which is selecting the best locations on the map, to thinking about economic incentives, let's say paying farmers, paying landholders a fixed rate for to incentivize tree planting or incentivize private land conservation, it will have very different results. And lastly, I wanted to also make the point about the difficulty in evaluating the success of some of these risk-sensitive planning approaches. Let's say we deploy these on the ground and then and then nothing happens. Well, actually nothing happens is a good thing, right? But how then we would attribute the success of some of these conservation activities back to the people who thought more carefully about risks? Because usually risks, when you think about risk, you think about things that failed, things that aren't successful, right? But if we thought more carefully about how we reward decision making that are risk sensitive, then things more explicitly about risk and uncertainty, that would really incentivize decision makers to use these tools when they are thinking about the global commitments to biodiversity and climate. So thank you for listening, and I look forward to questions and comments. Thank you.
Thank you very much, Frankie. Question floor.
That's great. That's a terrific talk. Thank you. I'm a big fan of flexible approaches, but I think one of the challenges that I often find is if the conservation tool takes a long time to have an impact. And marine protected areas is a good example of that. That adds a really severe constraint on your ability to be flexible when you know you've got this lag of benefit that means you won't actually get a benefit if you hold off to be more flexible. Those benefits will take even longer to kick in. So do you consider that as part of your strategy for evaluating?
Thanks for the question. So what's your name?
Peter.
Peter, right. So thanks, Peter, for the question. So for those online, the question relates to the flexible planning approaches that I've presented and the difficulty that decision makers face when they have benefits that come from a much later time. So when we use a flexible approach, a lot of times, for example, when we think about, let's say, some restoration or conservation, we put in protection now, and we are only able to realize the actual benefits on the ground 10, 20 years later, and that's highly variable and uncertain. And in that case, it's much harder for decision makers to think about keeping options open and flexible. Is that not your question?
Yeah, it creates a trade-off for them.
Sure.
Yeah.
So here, what we are working with are modeled benefits, obviously. So we are thinking about the projected benefits that we would get using a range of species distribution models under climate change, and really, here's where projections and mathematical models can help address some of the concerns here, because a lot of times we have to make decisions using projected benefits, and if we have to wait until the actual benefits to come out before adapting to our options, then it will create severe trade-offs, as you mentioned. But there's also a huge utility in thinking about some of the actual on-the-ground monitoring and evaluating the success, and also adaptive management approaches that utilize the information that we have right in conservation protections that we have in the first time step to continually improve on the decision. And to some extent, my work thinks a little bit more about that. So if we actually deploy some of the planning approaches here using the projected benefits, and then we invest in protection in the areas that we deem suitable and low risk in the first time step. And then we can observe the outcomes over in the future, such that in the future, we still have the options to use the knowledge that we have observed on the ground to improve actions there. So I think there's a strong case to apply some of these methods here, but there, of course, when we're making decisions at the first times, that we have to rely inevitably on modeled benefits rather than observed benefits that are collected through monitoring and adaptive management approaches.
So, sorry. So how do you think about costs in this? I noticed in the example in England, you had like overall social costs of carbon. Then you also had like costs from loss of agriculture. And so some of those are borne just by the landholders. Some of those are borne by global society. And I guess in Australia, you're talking about private land. So how do you? It seems like there's like asymmetries in all of these costs. How do you normalize?
Thanks. That's indeed a great question. So for those online, the question is about how I address costs and quantify the costs associated with ecosystem restoration and also conservation planning. So because in the UK case, we've got multiple costs that are associated with foreground agriculture, and also the cost of putting seeds on the ground and administering the forests, for example. And in Australia, thinking about private land conservation. So here in this context, in the UK case study, I modeled, I tried to think of that as a public cost, right? So that public costs are costs that are incurred to the general public as well as to the private landholder, right? So here, that's what we are doing is using a natural capital approach. We try to integrate all of the costs that are borne to public society into the decision making, such that we are trying to optimize for net benefits. So that's total benefits that society is receiving after the tree planting activities minus the total cost that borne by society, including the private landholder's cost to do that decisions. And what we're trying to do with the decision making is to maximize for these net benefits. But that's like not representative of the full picture, right? Because, for example, a private landholder might have might have a smaller subset of the costs borne to them compared to the public. For example, let's say the carbon sequestration services, we sequester some carbon, and that has a private benefit. You can sell that through carbon credits, but at the same time, there are public benefits there, and there might be a difference in terms of like the benefits there. And I fully understand that there is a challenge here. So in the Australia case study, I model the opportunity cost of the willingness to pay of these landholders for private land conservation. So these are only capturing the private costs. So we're assuming that there are other benefits to wildlife conservation, and if we also talk about the benefits of wildlife conservation in monetary terms and take that away from the private costs, that would result in much lower costs, and in fact, it could even lead to different decisions that we make in the top. But here in the Australian case study, I only focus on private costs. But that's a great question. Thank you. I hope that answers your question.
Just so it's in the UK case, some landholder loses $1 million worth of crops is no different. Like it's not treated any differently to like 100,000 people losing $1 million. The fact that like this is like private money being lost. You don't think about just the sort of public benefit portion of the private. If I lose $1 million, then society loses the taxes. But my $1 million isn't necessarily an issue for society as a whole.
Yeah, thanks. That's a great question. I think to summarize the question a little bit, it relates to equity concerns as well. So think about who are the winners and losers of this policy. Is that something you're thinking
I
about?
guess so, but I feel it's this might just be a naive question for like a non-economist, but it seems like when you're measuring the benefits to society from like financial value of the environment, it depends. Yeah, society doesn't benefit from one person, making $1 million in the same way that they benefit from. So if you lose that $1 million, society doesn't lose very much compared to, if it's some publicly owned asset, you lose $1 million worth of the publicly owned asset, that's all society loses $1 million. And, so there is an equity, but it's also just sort of measuring.
Yeah, that's right. So I think in the case study that presented here, we assume it's the same. So it's a private landlord with $1 million is equivalent to society. Everyone using society with 1 million people, everyone using $1, right? Yeah. But that's of course a simplification here, right? We are trying to maximize total benefits society is very fun. But that's different from what you're suggesting is that if everyone just simply uses $1 million, everyone in society just uses $1, the total changes in the happiness of the utility of society might be different from just one landlord using $1 million, because that landlord might have tens of millions of dollars, and using $1 million doesn't affect their utility as much as everyone in society using $1. Is that? And that's a complexity that I've not explicitly incorporated here, but it's a really important point and a vital point of discussion in our very
Yeah, well, I'm kind of thinking about this question and that like maybe if it's kind of more of a comment, sorry, but like if there's a way to like weight the two opposite outcomes, like we could probably, most of us in here, I hope would agree that the outcome that we don't address climate change sufficiently is a worse risk than accidentally spending extra $1 billion we didn't need to. And so I guess maybe it's kind of what the other question is getting at here. Like, is there a way that you could weight those outcomes and maybe give more weight, like maybe artificially inflate the risk of the outcome of not addressing climate change sufficiently and decrease how much we, for lack of a better way of putting it, like care about how much we lose? Like, can we weight those two sides of the equation somehow to give more emphasis to wanting a better climate change outcome?
Thanks. That's a great question. So that question is about how do we weight the possible outcomes of not failure to mitigate climate change versus a net loss to British society, for example, for incurring $10 billion pounds because let's say we plant too much trees and that takes food out of agriculture. That takes production out of agriculture. And that's a great question, I think. Because and something that it's a circularity here, where let's say in the UK example, we plant a lot of trees and that mitigates climate change. But then if it mitigates climate change, then we are in fact planting the wrong trees, and therefore there'll be a huge cost to society. But if there's a huge cost to society, then if we optimize it, then we would want to plant much less trees. If we want to plant much less trees, then climate change becomes not mitigated. So there's a circularity here that becomes really hard to model. But I also want to emphasize that the effects of tree planting to climate change is dependent not just on what the UK does. It also depends on what everyone else does, which is it gets increasingly hard to model the outcome. So let's say even if the UK plants 6 billion hectares of trees. I don't think they have 6 billion hectares of land, but anyways, we could still fail to mitigate climate change. We could still be digging up coal and fossil fuels out of the ground, and that contributes to our failure to mitigate climate change. So there are a lot of other variables here that we cannot fully address. In this case, I fixed the amount of carbon sequestration for the planting scenarios to sequester approximately the same amount of carbon every year, but that that question is still valid. So I'm just comparing tree planting scenarios that sequester the same amount of carbon, but the problem still exists of the circularity in the arguments here, and it becomes increasingly hard to model these effects. In economics, we call it endogenous effects, where A affects B and B affects A and vice versa.
Eliminating cost would make it more appealing to other countries to do the same thing, or more possible, so that's probably a benefit to worldwide climate mitigation. Yeah, anyway, thank you. Thank you.
Yeah, so first of all, great talk, thank you for coming across and giving it to us, and thanks to Brooke and Jonathan as well for coming through and coming back. I have one simple kind of question. I'm curious with the flexible approaches, do you assume that the same suite of options is available to you in the future as is now? Like, is there any sort of part of the model that says actually the suite of opportunities may be decreasing? I mean, maybe if you're thinking about reforestation, maybe it's increasing because we're taking more land and putting it in agriculture, but in lots of other circumstances, that suite isn't looking the same, and you're losing opportunities in the future.
Yeah.
You don't do something now.
Thanks. That's a great question. So just to repeat Daniel's question, it's relates to the flexible approach and things. The question is whether or not I assume the options for current protection for conservation is the same as the options that are available to future decision makers. As we might know that there are many other drivers that would reduce or increase the options that are available to decision makers. For example, deforestation, land clearing will continue. Let's say in New South Wales over 30 years, it's declined at 6%. We roughly estimated that, let's say if we assume current deforestation trends, that would lead to decrease in 6% of the total amount of habitats that are available for protection. And there are many other drivers, right? There could be a fundamentally increase in the land prices that increases the opportunity cost of farmers for protecting land and so on and so forth. But there also, of course, there could also be increasing opportunities as new buyers come into the or people restore the land and it makes it available for conservation in the future, right? So it could change in either direction. So what I've assumed here is that firstly, I've assumed that a roughly 6% decrease in the amount of options that are available over the 30-year time period, and that's why you see, like, one of the reasons why you see confidence bounds around these strategies that, depending on which properties are gone, it will have different effects on the strategy. But what I also explored was that if the future decision maker has indeed declining options, reducing the set of options continue to reduce due to land clearing, right? Because if we don't protect right now, then land is going to be cleared, and if we clear, then we can't protect in the future, right? So if that continues to decline, I found that we have to assume a much higher deforestation rate than what we are assuming in the historical rates in order for a flexible approach to not make sense. Not make sense being that it would not lead to net savings compared to a flexible or a robust approach. So we estimate that it would take around 80% or 90% of these options to be gone in order for us to not think about a flexible approach to make sense. So that is the reason why that is the reason why we still want to think about flexible approaches. Obviously, this part of the findings might not generalize to other case studies. For example, if we think about rainforests in Indonesia, for example, that we could be facing a much higher rate of decline, or maybe habitats are irreplaceable in some ways that such that the declines in options could occur much more rapidly. But here in this case, I demonstrate that flexible approach is still viable and still lead to net savings, even if we assume a much higher decline in the set of the options that are available to decision makers in the future.
Thank you so much, Frankie. That was really a wonderful presentation. I really